Hi, this talk is based on a joint work with Itai Arad from Technion and David Gosset from Waterloo, IQC, and PI. There are three central objects of this talk. One is that of spin system. A spin system is a collection of qubits or spins which are arranged on a regular lattice. So this picture shows a two-dimensional square lattice. For this talk, it's immaterial whether you could consider a two-dimensional hexagonal or triangular lattice, but it should be of a two-dimensional form. Given lattice of certain length n and l, the qubits they interact via what is known as a Hamiltonian, which is a giant matrix that acts on all these on the combined vector space of all these qubits, but it has a simple form. And this form is given by its decomposition as a sum over local terms. Each local term, for example, the one shown here, it acts non-trivially on a few qubits. So for instance, the Hij, it acts on this, all the qubits on this placket, and it acts as identity on everything except these four qubits. So given this form, which is known as a local Hamiltonian system, we can define what is known as a ground state of this system. A ground state is a quantum state that minimizes the eigenvalue of this Hamiltonian, and that eigenvalue is known as the ground energy that I'll call E0 in this talk. And the next notion that comes in is that of a spectral gap, is the difference between the second smallest and the smallest eigenvalue. That's the spectral gap of the Hamiltonian, and in this talk we'll assume that it's a constant. So there can be more than one ground state for this Hamiltonian, and that happens when there is a degeneracy, and that is also included in this set of ground states. We'll assume without loss of generality that each local term is a positive semi-definite matrix, and its eigenvalue is at most one, largest eigenvalue, which sort of captures the property that the energy is not too large in some small part of the system. This assumption can be always ensured by shifting the energy a little bit. So given these properties, the next concept that we'll need is that of entanglement entropy. So given a quantum state psi that lives on two systems A and B, the entanglement entropy measures the quantum correlation between the two parts. For pure states, entanglement entropy is defined as the entropy of the reduced density matrix on either systems. It doesn't matter which one you take. And this entropy is given by the von Neumann entropy. There's another entropy that often is useful. This is known as the main entropy. It's just log 1 over the largest eigenvalue of the reduced density matrix. So one example of this is when psi AB is a maximally entangled state between the two parts. In this case, the entanglement entropy is the same as min entropy, and this quantity is log of the dimension of the smaller system between the two, let's say A. The third notion that comes in is that of polymer approximation. This notion has been studied for over a century in mathematics and also more recently in computer science. And the goal here is to approximate functions which are not so well behaved with some nice functions such as polynomials. So in this picture, you see, for instance, the exponential function, or you see here a delta function, which peaks at certain value E0, which, if you recall, I have been calling as the ground energy so far. So that's what will be important. So given a function, the goal is to find this low degree polynomial that achieves an error epsilon for all x in some range. So we could ask, for instance, to approximate this function in a range like this, for instance. For the delta function, we can't really approximate too close to the point where the function takes large value because of discontinuity, but we'll assume that we're going to approximate the function either at this point or in certain range like this. It's well known by now that to approximate most nice functions, Chebyshev-based approximation is the best one, and it usually achieves the optimal approximation in terms of degree and the error epsilon. Now, the entanglement entropy, it often comes up in spin systems, quantum spin systems, and a standard question that has been around for a long time is how does the entropy scale of a quantum state on these spin systems? If you take a random quantum state, and if you take a partition of the system into two parts, A and A complement, let's say, with the partition being called the boundary of A over here, and the partition is shown in yellow. Random quantum states, they almost saturate the entropy. And the entropy scales roughly as the number of particles you see on this side. For gapped ground states, that means the ground states of Hamiltonians which have a spectral gap, Arad conjecture posits that the entropy scales in a much simpler manner, and it scales as the length of the boundary of the system, which can be counted as the number of plaquettes that cross. It doesn't have to be plaquette, it depends on the kind of Hamiltonian you're thinking about, but just the number of Hamiltonian terms that cross the boundary. So usually the boundary is much smaller than the volume, and thus Arad conjecture posits that the gapped ground states, which I should actually call this in this manner, the gapped ground states, they're really special. They're not like random quantum states. So this conjecture is believed to be true for all finite dimensions. Thus far, in full generality, it has only been shown in 1D by Hastings' seminal result from 2008, and this has led to several important consequences that came a few years afterwards. But this question so far is open in 2 dimensions in the full generality. Now, polymer approximation has also been a pretty useful notion in spin systems. And here we really see the power of Chebyshev approximation. For example, the tool of Chebyshev approximation has been useful in pinning down the correlation length in frustration-free spin systems. And these systems are those which have the property that the ground state of the full Hamiltonian is the ground state of each local term. That is, the ground state satisfies all the local terms. So you could think of it as the quantum analog of satisfied CSPs. Frustrated systems are the quantum analogs of unsatisfied CSPs, where the ground state does not satisfy each local term. So for general systems, the correlation length scales as 1 over the gap, as shown by these authors long back. But Gosset and Huang, using the Chebyshev approximation and the improvements that come along, showed that the correlation actually scales in this following manner, which is tight. Similarly, the Arad laws in 1D have benefited a lot from this point of view, and the original result of Hastings was exponentially improved by these authors using again Chebyshev approximation. So this result is again along the similar line, showing the power of polynomial approximations. Here we'll go beyond Chebyshev approximation, as I'll describe in the coming slides. But the main result is that the unique ground states of locally gapped frustration-free Hamiltonians in 2 dimensions, they satisfy an Arad law across what I've been calling as a vertical cut. That means the entropy scales as the boundary times 1 plus something that goes to 0. So this expression over here is 1 asymptotically instead of 2. That's for the volume. Now, uniqueness is not necessary. And in fact, you can always pay the price of log the dimension of the ground space if you want to prove similar result for non-unique ground states. The notion of local gap, it's basically the local gap, it's the spectral gap of the Hamiltonian defined on all rectangles that look like this across the cut. So given this cut, all the rectangles that go in this way, we look at the Hamiltonian and we sum over all the terms that belong to the rectangle, and we require that the spectral gap is constant for all these regions. So under these assumptions, frustration freeness and local gap, we can show this property, Arad law property in 2 dimensions. Let me spend this slide giving an intuition for the proof. So let's start with the question as to why Arad law is believed to be true at all on lattices. And the reason basically comes from this intuition. The intuition comes from the notion of correlation length. If you look at the region A, if the correlation length is small, then you'd expect that all the quantum correlation from A only goes as far as the extended boundary B. That's roughly of the size of 1 over gap. So entropy of the quantum state on A, you'd expect only extends to the region D, and that's a small region. That's roughly the area divided by the gap. Unfortunately, this intuition has not been shown to be true in 2 dimension at all. It's only formally established in 1D, where the actual result scales in this manner, exponentially in 1 over the gap instead of 1 over gap. And such a result is not known at all in 2 dimensions. So we don't know how to formalize the intuition that correlation length should be the source of area law. But correlation length is in fact a local property, which is the intuition. In some sense, the correlation should be local. And our result is to replace the notion of correlation length with a different notion of locality, which is that of optimal polynomial approximation. So at a very high level, what we show is that the optimal polynomial approximation that I will describe in the coming slides, along the boundary of this cut of this partition, implies an area law for the region A. And the way we'll prove area law is that we'll first construct optimal polynomial approximation along the boundary, which is an effective 1D system, and we'll use that to we'll lift it to a 2-dimensional area law. Let me mention some prior works in the past that have shown area law under different assumptions, such as particle-like excitation or small number of low-energy eigenstates, frustration freeness, and spin half system with nearest neighbor interaction, adiabatic assumptions, specific assumptions, and so on. These assumptions are incomparable as far as we know with the assumption of local gap or also the assumption of spectral gap. Area law is known to be false in high dimensions, especially on very general complex looking graphs, as shown by the result of Aharonov et al. In 2014. So in the remaining talk, I'll describe how do we really prove such a result. And it's based on the technique that starts from Hastings and followed by, developed further by several authors. So this is the notion of Schmidt rank of an approximation to the ground state. The Schmidt rank of an operator K, which acts on the full system across a cut, captures the entangling power of the operator. And formally, it's defined as the smallest number D, such that you can write K as a sum of product operators. These operators don't create any entanglement. And if the sum is small, then you create little entanglement. So the goal in all the results so far is to find a K that approximates the ground state and has a small Schmidt rank, and then hope from there that area law can be shown. And there are 2 kinds of approximation that you could imagine. One approximation is the L1 approximation, that K in fact approximates ground state in L1 distance. But this is usually not very general, and it only works under the assumption of particle-like excitation. But if you are looking for more general assumption, then we have to relax the notion of approximation, make it much weaker, and we have to ask for L infinity approximation, that the operator K approximates the ground state with L infinity distance epsilon. So that's the assumption that we'll work with. And under this assumption, which is where the notion of approximate ground state projector comes in. So the operator K is known as the AGSP, which approximates ground state in this manner. It was shown by Arad, and Vazirani in 2012 that if the Schmidt rank of this operator is smaller than 1 over the approximation, then we can bound the entanglement entropy by twice the log the Schmidt rank. So the pursuit of area law since then has been to find an operator that first satisfies this property, next also has a low Schmidt rank. Having both is the central challenge of this problem. So this is where the polynomial approximation comes in, and this is also an idea that comes from the work of Arad and Vazirani. And here the idea is that if we have an operator with small degree in some sense, then it will have a low Schmidt rank. At a very high level, a small degree means that the polynomial is a linear combination of small number of terms of the Hamiltonian, and hence each such term will not increase spin rank by that much. So the overall increase will be exponential in the degree. Of course, the issue is that we don't know, we need to control the number of terms in the sum as well, but I will not discuss that here. So now let's look at the goal again. So we are given the ground state, which can be captured by this blue function f, which as before is the delta function that peaks at the energy 0, which is my E naught. And we are looking for a low degree approximation to this function, which peaks at 0 and it stays small at the rest of the spectrum. The difference from 0 and gap comes from the spectral gap assumption of the Hamiltonian, which is omega 1 as mentioned earlier, and the x-axis of the spectrum. So given this, Chebyshev polynomial is the best polynomial of the Hamiltonian that achieves this approximation. And roughly the degree is the square root of the max energy times log 1 over epsilon, where epsilon is the error that we have. Now this technique works very well. This polynomial works very well in one dimension, but let's see what's the issue in 2 dimensions. Well, the first issue is that the max energy could be very, very large, but let's totally ignore that at this moment. Let's say somehow we manage to restrict to the Hamiltonian along the boundary, which means that the max energy of the Hamiltonian would be at most the size of the boundary times some constant, so that we square root of the boundary, and the degree would be log 1 over epsilon. The issue is that this degree is too high for a given epsilon. The Schmidt rank is roughly exponential of the degree, which is roughly 1 over epsilon to the square root of degree, square root of the boundary. Since the length of boundary is much more than 1, this number is much more than 1 over epsilon. In one dimension, boundary is a constant, so there's not much of a difference here. But in 2 dimension, the difference really comes in just from the large size of this boundary. So the key bottleneck is that the Chebyshev approximation is known to be optimal approximation of to the ground state. So there really seems to be no way moving forward, and it seems that the polynomial approximation approach is not the right one for proving 2D errors. But our starting point is observation that if we look at what is known as a commuting Hamiltonian, which is sort of a classical like Hamiltonian, then area law holds. Commuting simply means that all the terms mutually commute, or you can find a basis in which each local term sort of acts classically. It diagonalizes. For such Hamiltonians, the spectrum looks more than just what we see in this picture, being dense here and being 0, one eigenvalue being here and the rest all in this region. The spectrum has more structure, and the structure is the following form, that the eigenvalues are at regular interval, essentially at integer points. So given this, it's well known through these works that we can beat Chebyshev approximation, and we can get a degree that scales as square root of boundary times log 1 epsilon, where note that log 1 epsilon is inside the square root compared to here. So this seemingly technical point seems to make a lot of difference. And if we choose error to be small enough, that's e to the minus roughly the boundary length up to a big constant here, then square root takes care of the big constant, makes it a square root, and degree becomes something of this form, Schmidt rank is of this form, and we can choose, and choosing epsilon small enough, we can get Schmidt rank to be roughly this, which becomes much smaller than 1 over epsilon. Now the issue is that this is great for commuting case, but we already know in area law for commuting case, and in the non-commuting case, even under local gap assumption, this spectrum is simply not true. The spectrum of the Hamiltonian doesn't look like this at all. Despite this, we show that's the main technical result, that we can still get such polynomial approximation that I'll call the optimal polynomial approximation, which I quickly mentioned in one of the early slides. And we show that one-dimensional locally gapped frustration-free Hamiltonians admit an optimal polynomial approximation. More precisely, given the ground space of a 1D FF Hamiltonian with local gap constant, there exists a multivariate polynomial of the Hamiltonian terms, such that the polynomial well approximates the ground state with error epsilon, and the degree of the polynomial is of the right form with log 1 or epsilon inside the square root, which mimics this behavior without having to assume integer spectrum. So the Chebyshev bottleneck that I mentioned earlier gets resolved at a very high level by going to multivariate polynomials. But of course, that's something not clear at all upright. So now, given this property, now I'll describe how do we lift this 1D construction to 2D. And this lifting is done by the idea of truncation, which was originally introduced by these authors in the context of 1D systems. So what we do is that we essentially construct an effective Hamiltonian along the boundary by taking a region of constant size along the boundary, and we truncate row by row all the Hamiltonian terms that are far from the boundary. Let me mention that as a technical point, that this is not really constant. It grows a little bit as a function of the boundary. Similarly, this is not really up to n, up to all epsilon. There's a little bit of dependence on n, and that leads to our area law with a tiny correction that goes to 0. So that's a side technical point. But for this purpose of the talk, for the purpose of this talk, let's just think of this as a constant size. And this property, along with what we call the merged property, which means that we can combine the ground spaces together with very small error. Ground space of first row and another row can be combined with a very small error. This property, which is ensured by local gap, along with truncation, helps us lift this result to 2 dimensions. Now, that's whole of the description of the construction. Now let me conclude with some open questions. So some very natural next open questions are: can we prove the same result for 2-dimensional systems, which are frustrated, which are not necessarily frustration free, and we don't know how to do that. It seems that the central bottleneck there is the local gap assumption, and then next important question, probably more than this, is which, although it's not very clear, it would be that maybe we should be able to remove the local gap assumption and only show the results with the global gap assumption. A natural conjecture here is that maybe local gap implies global gap. This is violated in certain specific systems that are known as edge states, where we have diagonal bipartition instead of vertical bipartition, or a bipartition that looks rectangular. But it's easy to get around these bipartitions and prove area law, despite the fact that this is not true, local gap. So it's possible that maybe for some regular bipartitions of the system, local gap is indeed possible. It may imply global gap. Another question is, can we prove area law for frustration-free systems in 3 dimensions? Here again, the central question is, can we construct these polynomials which are optimal in 2 dimensions, which can be lifted to 3 dimensions? Finally, another very interesting question is, can we show that 2-dimensional locally gapped ground states can be represented by paps of small bond dimension? And that's all. Thanks.